So when you have an indeterminate axial member, you're not just limited to the stiffness or displacement method covered in chapter 4.4 of your book. There's actually multiple different methods, but the only other method that we're going to cover in this class is also called the force flexibility method, which is discussed in chapter 4.5. So chapter 4.4 is a more traditional stiffness displacement method. Some people find the force flexibility method a bit more intuitive, and so you might be told which way to do it on homework or an exam, but if you're not, then you're free to do whichever way is more comfortable to you. So the example problem that we're going to go over right now is the exact same example problem that we used for the stiffness displacement method. We have a prismatic column made out of a homogeneous material that's supported between two rigid supports at A and B. Point C at some intermediate point, not necessarily right in the middle, has a point load P applied to it that's forced downwards. And so in this case, we're asked to find either the normal force in member AC and the normal force in member BC. Once we calculate one, we can just use statics to calculate the other, so either would be fine. So in this case, we're actually going to focus on the reaction up at the top, and then like I said, once you have the reaction at the top, you could calculate the reaction at the bottom as well too. And so the force flexibility method kind of switches up the analysis compared to the stiffness displacement method. Whereas with stiffness displacement, the first thing that you do is you make some section cuts, you use statics to try to relate those internal forces. With the force flexibility method, the first thing that we look at is compatibility, but we look at it in a different way than you might expect. So this actually involves what we call a straw man approach, where we take one of these supports away and try to figure out how much would this deflect if the support wasn't there. And so this is all under the guise of step number one, which is compatibility. So for this step, we need to create what's called a primary system, which simply means that we're going to choose one of these two supports to take away. So we need to create our primary system. So it's up to you, whichever support you want to take away. You just have to make sure that whichever support you take away, the system is still stable. So here I'm going to choose, actually I'll choose to take away the support at the bottom. It doesn't really make any difference. And so I'm going to make my primary system, so you just remove one support. And we actually need to consider the primary system with two different loadings on it. So the first loading, I have my primary system. I still have my support at point A at the top, and I'm going to draw that primary system twice. So I've chosen to remove the support at the bottom, but it's, like I said, arbitrary. So the two different types of loads that we have to consider, the first is the actual loading. So we look back at our original system and we say, we took away the support down here, but I'm going to consider this external load is still being applied. So I'm still going to apply that point load P to this primary system, but I need to keep track of how much deflection in the primary system happens wherever I took that support away. So basically what we're saying is, if I didn't have the support down here, how much deflection would I get due to that external loading? So we remove this, we see how much deflection would occur if I had that no support at the bottom. It's kind of like, how much does it want to deflect? And the second consideration would be, well, I need to add some loading to this primary system so that the summation, the superposition of those two together ends up with zero deflection at that free tip. the total deflection needs to equal 0 because in real life, that's how much deflection we have here. It wants to deflect, let's say it wants to deflect down an inch. We know something has to push it back up an inch because in reality, when I add those two together, the total displacement has to be 0. And so this total displacement is going to be the displacement due to the external load P plus the displacement due to some redundant support reaction. And so that redundant support reaction I will just call R, and that's what we apply to this second primary system here. So you're free to guess which way you think the reaction is going to go. In this case, it's pretty clear that it's going to be pointed up. You could also draw it consistent with what our sign convention is, but it's really a support reaction and reaction and external load. So there's no real sign convention for it. So you're free to do it whichever way you want. I will go ahead and draw it the way that it's clear that it's going to be going. I will call this R sub B. Okay. And then we need to keep track of how much this will deflect. And so the deflection here, the way that I have it drawn, I need to keep track of how much this wants to get longer as well. And that could be a little bit confusing. The point is that whichever, when these two add up together, they need to equal 0. If I drew it the other way, then they would need to be equal in magnitude and in sign. I'm trying to be at least consistent with the way that we define deflection. In this case, these are both shown as the assumed positive direction. Okay, so with that in mind, this plus this has to equal 0 because the total deflection is equal to 0. So all that we have right now is everything in terms of deltas, but I can use mechanics of materials to tell me what delta is going to be, what that equation is going to look like. And so again, this is going to be, this is what we call our redundant support reaction is R sub B. And we apply it wherever we took away the support from the original system. Again, we're keeping track of the deflection on both, and it's important for our equation over there that we assume the same direction for each of these. We're consistent, and we assume positive for elongation. It's very easy to make sign mistakes, and so we'll try to avoid that. Okay, so for each of these, we can use our fundamental deformation equation for an axial member that's subject to a constant normal force over a constant cross-sectional area, which is simply the summation of NL over AE. There's no need to do the integral form of the equation here. It's going to be constant normal force for a set distance. And so we can just sum up the results. And so in this case, if I were to look at the internal normal force diagram for this loading, if I were to plot out the internal normal force across the entire height, I would find that if I made a section cut through this free end right there, there's no forces acting down here. This is just a displacement. No forces down here. If I made a section cut right through there, I would get 0 normal force for the bottom portion of this beam. In the top, I would get a constant positive value of P. I'd have a constant positive value of P. If I made a section cut right there, I'd have my normal force pointed up. And I'm not going to go through the free body diagrams, but suffice it to say, this would be my normal force diagram, a constant value of P for member AC, and no tension in the bottom. Again, remember, this is a fake system right here. I know that in reality, I'll have some force over here, but for this primary system subject to a point load, my reaction up at the top is just going to be, the reaction at A is going to be P in the opposite direction, and so this will be my normal force diagram. For this second loading on the primary system, I have R sub B pointed up, and so my support reaction up at the top is just going to be equal to R sub B. And it's in compression, I'll get a constant negative normal force the entire distance. It'll be equal to minus R sub B. So here I get tension in the top, nothing on the bottom. Here I get constant constant compression the entire height. And so if I want to calculate delta P, it's just equal to the summation of NL over AE for each of these sections. Down here, there's no normal force, and so that's going to be equal to 0 for member BC. For member AC, it's going to be NL over AE. N just happens to be equal to P, and L is LAB, so I get N is just equal to P times the length of member AC, divided by the area of member AC, times the modulus of member AC. Again, plus 0 because there's no deformation of this bottom portion because there's no normal force. Over here, the deformation due to the redundant support reaction is the same thing, equal to summation of NL over AE. Here I have a constant normal force the entire height of this column, and so because the area, cross-sectional area for both of the top and the bottom are the same, and the modulus of elasticity is same for the top and the bottom, I can just say the length is the entire length of this member, and the internal normal force is equal to minus R sub B. Equals minus R sub B times the total length divided by, I'll just say A and E now because they're the same whether it's AC or BC, and I'll do the same over here. Just A and E. In this case, the areas are the same, the modulus is the same, so there's no reason to keep the distinction up. And so if that's the case, I can now plug these values into this equation right here. And I can say that the total deflection, which is equal to 0, equals the change in length that would happen due to the point load if the support wasn't there, which is P times LAC divided by AE, plus the deflection due to the redundant support reaction that's necessary to get this back to 0 displacement, which would be minus R sub B times L divided by AE. So I can multiply by AE, get rid of the denominators. I can do a little bit of arithmetic reconfiguration, and I get R sub B equals P times LAC divided by the total length. So that's the reaction at B. That is this force right here. So this force right here is equal to P times LAC divided by L. And so if I want to find the internal normal force in member BC right there, I could just make a section cut. I could draw a free body diagram. I know that my support reaction is P times LAC divided by L. And I know that my internal normal force BC acting on the section cut is pointed away from the section cut as my assumed direction. And so now when I sum the forces vertically, I get that NBC is going to have to be equal to minus P times LAC divided by L. So we get to the correct answer in a very different way. And simply step number 2 in this situation, step number 2 is where we start using equilibrium, but we only use equilibrium to then, once we've gotten one, say, support reaction, then I can solve for the other support reactions as a result. So this would be P times LBC divided by L. I just use statics. I'd sum the forces vertically to find what that support reaction is at point A at the top. So this straw man approach, some people find it more intuitive, some people aren't as comfortable with it. I want you to be comfortable using both. You might be instructed to use one or the other on the exam or on the homework. But this way, all that we're doing is we're taking away a support and we're figuring out how much would it deflect if that support wasn't there. So let's say that we find that it's going to deflect 1 inch if the support is not there. We know in reality it's not going to happen, and the thing that's keeping it from happening is this redundant support reaction is pushing back up exactly enough to then cause an inch of contraction, an inch of compression in that member. And we can just look at both of those separately and then add the effects together. And you'll notice the actual normal force diagram, if we were to plot those out, so the actual normal force diagram compared to the normal force diagram due to the external load on the primary system and the normal force diagram due to the redundant support reaction on that primary system. If we were to look at those, and I could just say the total normal force is equal to the normal force on the primary system due to the point load plus the normal force on the primary system due to the redundant support reaction, the actual normal force diagram over the entire length looks like this, where we get, compression on the bottom. Let me switch that around. We actually get compression in the bottom of the member, and we get tension on the top. So down here in this bottom section, where P is pushing down, we get compression in the bottom, and as a result, we get tension in the top. The normal force diagram here is all positive. For the primary system with only the point load on it, I just get tension in this member, but it's greater tension than what we see right here. I just get pure tension in the top. But I add together the normal force diagram due to the redundant support force, and that's compression the entire height of this member. So that's some negative value here. If I add this to this, I get this diagram right there. And so the force flexibility method is really all about splitting up the load effects and the redundant support reaction effects separately, just adding them together to get the total picture of what's happening with the assembly.